So it's about time to have our seminar. Today we have four presenters. And let's welcome the first presenter, Li Yanrong.
Hello everyone, my presentation is lightweight deep learning music emotion recognition model. I'm Yan Yonglin and my advisor is Dr. Chen Kai. Let's take a look at our outline, which includes background and motivation, proposed method, results, conclusion, and reference. With the global demographic population aging has become a phenomenon that cannot be ignored, and more elderly people are facing loneliness and depression. This emotional problem not only affects their mental health, but also reduces their quality of life and satisfaction. Music has been an important medium of conveying emotions since ancient times and can touch people's hearts. Therefore, in order to elevate the emotional progress of the elderly by recognizing the different emotional characteristics of music and playing the corresponding music that has been identified by our music emotion recognition. According to the current emotional state of the elderly, we can adjust and improve their mood. Advancement in technology has made companion robots a valuable tool for enhancing the emotional well-being and quality of life of the elderly. This study utilized these robots, integrating advanced music emotion recognition technology to enable them to play music that aligns with the user's current emotional state. This involves not only identifying emotion within the music, but also selecting terms that positively influence the user's mood, requiring the robots to process and respond to this emotion in real time. A significant challenge is that many existing music emotion recognition models are too complex and computationally demanding to be effectively deployed on our robot Lambo Junior 2. With limited hardware capabilities, this model often exceeds the processing and storage capabilities of our robots. Thus, this study focused on developing a lightweight music emotion recognition model that is both effective and suitable for operation on robots with constrained hardware resources. Let's explore the emotion theory model we utilize to classify and recognize emotions in music. Our method is anchored in Bayes' erosion model, a two-dimensional framework extensively employed to represent and analyze emotions. Bayes measures the positivity or negativity of emotions, with positive emotions like happiness, excitement, and satisfaction, and negative ones like sadness, anger, and fear. Arousal quantifies the intensity or activation level of emotions, with high arousal including states like excitement and anxiety, and low arousal inhibition, calmness, and relaxation. We utilize two data sets for our study. The first is the MediaAble database for emotional melodies in music, which comprises 1,800 songs with emotional annotations. Each feature extraction, we employ male frequency capture coefficients, one of the most prevalent technique in music analysis. MSC's effective mimic how the human auditory system perceives sounds by mapping audio signal to the male scale. This technique allows us to pinpoint key music features. LNCC process involves several steps. Pre-emphasis, where we apply a high-pass filter to accentuate high-frequency components. Frame, where the audio is segmented into small frames lasting to 20 to 40 milliseconds each. Windowing, where the Hamming window is applied to each frame to minimize edge.
眼前你所看到的画面并不在地球上。
Phase Fourier transform, which transform this signal from the time domain to the frequency domain, producing a spectrogram. Male scale filtering, where triangular bandpass filter makes the spectrogram to the male scale, mimicking human frequency perception. Logarithmic operation, which amplifies the feature by applying a logarithmic transformation to the output of the male filter. Finally, a discrete cosine transform converts these features into MFCCs, encapsulating the music's core emotional characteristics. Let's talk our model structure and how it processes audio features to estimate balance and Roseau value. The layer 1 to layer 4 are 1D convolution neural network with 128 filters and different kernel size, designed to capture local temporal features. As the audio data progresses, it passes through additional 1D CNN layer with varying kernel life and strength, which can help downsample the signal, increasing the receptive field while refining the audio features. After each convolution layer, batch normalization, review activation, and dropout are applied to standardized data distribution, introduce non-linearity and get overfitting. The process data then enters a get recurrent unit, which captures sequential filters and temporal dependencies instead of the fully connected layer. We employ global average pooling, which computes the average of each filter, providing a compact representation that simplifies the final prediction process. Finally, the fully connected layer uploads the balance and Roseau value, translating the then feature into precise measurement of the music emotional traits. The get recurrent unit is a variant of the recurrent neural network. It is particularly effective for processing sequential data. It includes two primary gates: the update gate, which controls the extent of new information updating the hidden state, and the reset gate, which determines how much previous information to forget. Allowing the network flexibility in processing new data, this gate helps manage the flow of information, ensuring the final hidden state accurately reflects both past and newly acquired data. We use Lumin square error as a metric of our model evaluation. RMSE is an important metric for measuring the difference between a model's predicted value and actual value. RMSE is known for its sensitivity to prediction errors and unit consistency, making it particularly used for highlighting large discrepancies in prediction and easy to interpret. It is widely used to evaluate the performance of regression model, helping us quantify the accuracy of predictions. It also measures the performance of various facial and voice emotion recognition research is 91%, successfully achieved in the goal of implementing this function on the companion robot. We propose a lightweight music emotion recognition model that outperform other models on the PNE model dataset. However, it lags slightly behind on the thin dataset. Despite this, our model is significantly smaller than other models in terms of parameters and plots, demonstrating its clear efficiency advantage. Is a reference. Thanks for your listening.
Thank you for your presentation. I would like to open the floor to the questions. So,
Why use GRU? Because GRU use a smaller number of parameters than STM or other RNN. It is more compatible to be used for the purpose of companion robots.
okay, thank you.
Thank you for your presentation. And you mentioned that you use MMCC to extract the features from audio, but it is not doing for me. And I'm confused how many MMCC you have taken.
The first 40 MSCs were taken because the first 40 MSCs are sufficient for musical mood recognition.
I'm curious what kind of hardware you have in the Zenbo Junior robot. What CPU or GPU you use in the Zenbo robot?
I forget. Yeah.
No problem.
Thank you for your presentation. Let's welcome the next presenter, Zhang Jiachen.
Good morning, ladies and gentlemen. My name is Zhang Jiachen. My speech topic is quad bias array demonstrating using residual string transformer channel attention network. And my advisor is Professor Kang Yi Wei. And this is my outline for today. The introduction. So what is the bias array? Capturing RGB values simultaneously on a single pixel requires complex optical and sensor design, which increase the complexity and the cost of image processing. A bias array simplifies this process by alternating the arrangement of different color arrays while maintaining high quality color image. And what is the quad bias array? The quad bias array clusters 4 adjacent pixels with the same color filter, thereby achieving high sensitivity and resolution within a single sensor. This enhances image quality, particularly in low light conditions, providing smartphone users with the ability to capture stunning photo and video while reducing noise and pleasing clarity. And demosaicing. Most modern digital cameras record only one color channel per pixel. And in order to recover this missing channel, the image demosaicing models are proposed to reconstruct a four-color image from a one-channel mosaic image. And in this presentation, we explore the application of spin transformer network to quad-phire array demosaicing. By adapting transformer-based method, we aim to enhance demosaicing performance and achieve superior image quality. The figure below shows the purpose of the demosaicing task. The image on the left is a single channel image, and the one on the right is a four-color image. And this conversion process is called demosaicing. Related work. First is the traditional mathematical model-based method, based on signal processing techniques and interpolation methods, such as bilinear interpolation, cubic interpolation. However, they may introduce some blurring or artificial artifacts when handling complex textures and edges. The figure below is a simple example of a traditional interpolation method used for demosaicing. These are different weight metrics which apply based on various conditions and finally calculate the RGB value for each pixel. Due to the diversity of the real world, the restoration effect is often not ideal. And a learning-based method. Training models to predict missing color information from single-channel color data, allowing for adaptive adjustment based on different scenes and lighting conditions. They typically reduce or eliminate artifacts that may occur in traditional methods, resulting in more natural and realistic image. In the framework below is an end-to-end convolutional network. Its full name is Spatial Asymmetric Tension Generative Adversarial Network. They propose a novel asymmetric convolutional operation block, which can extract a sequence of vertical and horizontal feature maps, which can reduce visual artifacts from reconstruct full color image. And due to the significant progress of transformer models in various domains in recent years, we decided to apply it to quad-phire array demosaicing. And this is the full framework. The entire model can be divided into three parts. The first part is the shallow feature extraction part, which conducts shallow level feature extraction using one convolutional method to map the image space into a higher dimensional feature space. And the second part in the middle is deep feature extraction, which involves deep level feature extraction and is composed of several swing transformer blocks. And due to the GPU memory limit, we use 3 swing transformer blocks in this research. And the third part is the image reconstruction part, where convolution is also used to reconstruct feature into image. And result and conclusion. In this paper, we explore an application of swing transformer-based model to quad-phire image demosaicing. The result indicates that the model indeed performs better in solving the mosaic removal problem. However, the PSNR score only shows a slight improvement compared to the previous convolutional-based model, while the SSIM score decreased and the runtime increased. Therefore, there is still much room for improvement in this research. And the future work. Since the model is based on Swing IR, which primarily focus on image restoration tests, while demonstrating deal with single-channel image processing. There are slight differences in the details. So in the future, exploring novel loss function will be one of the main approach for constructing more optimized model to enhance PSNR score. And we use the transformer-based model, but the PSNR score only shows a slight improvement. But we only use the small part of the Swing IR framework, and there are much bigger Swing IR framework in the IEEE, so I think we have a chance to enhance the PSNR score in the future by this model. Yes, and that's my presentation. Thank you for your attention.
Thank you for your presentation. So any questions from the floor?
I'm curious, how do you get your ground truth? Because the image is taken from camera, and then how the ground truth is made. Is it using a model-based interpolation?
The ground truth is, so first we have the data set, like we use in this research is called DBI2K, and then we use some algorithm to eliminate some channel from the ground truth image, so it will become the quad array term.
Okay, thank you.
Okay, may I have some more questions? Would you please let me get to the result page? So here you give us three different index measurement: BSNR, SSIM, and the run time, right?
Yes.
So may I know what is the main object of your research? If you provide the runtime elements, hopefully you want to achieve like a real-time image restoration or what?
My object is to make the PSNR score as big as I can, and the runtime. We hope to reduce the runtime because every time you take a picture, if the runtime is too long, it will be like annoying.
Then if based on what you say to me now, I mean the PSNR you have the slight improvement, right?
Yes.
But if your runtime quite, or I would say the far behind the another state of artifacts.
Yes.
Okay. So any strategy for you to improve this? I mean in terms of the runtime.
I think I can limit this can reduce the runtime, but you need to make a balance between the PSNR score and runtime. So if we reduce the runtime too much, and maybe the PSNR score won't win the SA game.
Okay. Thank you.
Thank you.
Thank you for your presentation. And let's welcome the next presenter, 谢君怡。
In the topic I would like to introduce today is the automation and system development. Autonomous Charging for EDV and my advisor is Professor Shen Yichen. And this is my outline. In this study, we focus on the overall system components, visual system, motor system, and autonomous mobile robot system. The visual system includes design for YOLO, PMP, and the grading network. Finally, this study used the PBO means for the motion control. With the fusion development of EV technology and the Russian environmental consciousness, electrical vehicle has come more attention in recent years. And the issue of sensing charging type is slowly emerging. And this is the graph diagram detailing the entry system which includes the camera for EV charging socket, consistency for control the MMR and operator during the charging test. And this is a physical attacker diagram. And use the interface for to command the MR and the operator to circulate to the functionality of the vehicle for the purpose of charging. And about the visual system, the flow chart of the virtual system is as follows. This includes YOLO for detect the type of charging socket and obtain bounding box information. Then each undergoes image host sync and in loops fitting to obtain the center of the vector circle, followed by PLP calculation and final compensatory using CPM. The PLP is the primarily used method for calculating the relative portion and orientation between a camera and object. The PMP solution mainly computes these 7 points on the upper half of the CCS2 socket. And to better match real-world charging, we choose to use the PMP algorithm instead of local test to obtain coordinate information. However, it was nothing less is less introduce greater error. In testing, demonstrate excellent performance in discrete 3D space. Therefore, we designed a compensatory network, CPM, to collect the real-time performance of the system. We did not use neural network to compare about the rotation and going angle about the XYZ axis. And these are the simulation result of CPSM. The top part shows the result of the test case. Indicates the main correction is made in the lead axis. After computation, the coordinates are close to particle. In the bottom part shows the relationship between the number of iterations and the error. And reinforcement learning is a file of machine learning in AI. Its main concept is to learn to perform a task correctly by iterating interaction with an environment to obtain the best solution. This trial and error learning enables computers to make a range of decisions without human intervention. The internal system consists of 5 parts: agent, state, reward, action, and environment. And the state space was designed to consist of the 3 axes. 3 axes distance between the operators and operator and the particle. And the action space consists of the 3 axes, locals and the operator and the operator. And about the partial dimension in controlling the operators and operator, the system output has been modified by Pn to approximate the output value. Pn replaces the point we want to move to define as the point from the view state plus the local mobility by the time differential. And about the reward, there are the 4 reward functions we designed for the displacement. First is the distance reward function, and the second is the direct reward function, and the array reward function, and compression reward function. Their composing is shown in the lower right diagram, where the reward value increases as it gets closer to the target point. And the PPO is the improved evolution of policy grading, and primarily focus on safety and supporting credit ratio between the new and old policy. And this is about PPO architecture. Include ether network, PD network, and that function is the upper left. In the explosion part, entropy is used to regulate introspection rather than relation and loss to the action. And this is the simulation result. It can be observed as the number of iterations increase the reward value. Also increase sensitivity, and the hyperparameter of the simulation shown in the bottom left. And about the future work, in the future we will apply our increment effect to ensure the success of distribution reinforcement learning on robotic arm, and practical compute the place of inserting the charges into the socket. And about the algorithm, we will also compare with other diffusion force algorithms such as DPG. And in this study, and about conclusion, this study, a self design subjects model PLD, CKN, and other. And a deep reinforcement learning algorithm is used to control the calculator plus design reward function that show good performance in simulation. And thank you for coming.
Thank you for the presentation. So may I open the floor to questions?
There are many types of EV sockets. Is there only one type you use?
In your plan, we will add another EV socket is the type 1, and which is the SD socket.
CCS2 has 9 holes. Why only use the upper 7 holes for CFD calculation?
Because we want to increase the degree of the system that can be, and some will move and the intersocket will not be captured.
Any other questions? Okay, thank you for your presentation. If no questions, let's welcome the last presenter, Jim Wei.
Hello everyone, I'm Yan Wei. Today I will introduce my research, lightweight deep learning emotion recognition system based on facial and speech features. And this is my outline. I will introduce my project, methodology, result, and conclusion. Because of the increasing elderly population, especially the rise in dementia and depression patients, has made elderly care an urgent issue. There is a growing global demand for companion and caregiving robots. These robots, especially companion robots like Bimbo, provide social support for the elderly, alleviate loneliness, enhance happiness, and have a positive impact on their mental and emotional well-being. However, companion robots are not yet capable of fully replacing human companions, and companion robots sold in the market do not have exceptionally capable hardware resources, primarily due to cost considerations. Many of these robots have limited processing power and storage capacity, which may prevent them from supporting complex or computationally expensive neural network models. Whether recognizing human emotion through facial expression or voice, the features and characteristics related to emotions in a video often appear in various parts of the complete video. However, the changes in features before and after the video are significant clues for extracting emotion features. Therefore, this study used a complete video segment to extract both facial and voice features, rather than a single image or a short audio clip. However, processing the temporal relationships in data will lead to
excessively high computational costs for neural networks, particularly in the area of facial emotion recognition. This makes it challenging to implement the state-of-the-art methods in companion robots with limited computational resources. Therefore, reducing the computational cost of neural networks is a critical issue. And first, I will introduce methodology capital conditions. MFCC is a set of crucial coefficients used to establish the net frequency spectrum of an audio signal. By analyzing segments of the audio signal, we obtain a spectrum that represents the characteristics of the signal. MFCC is derived from this spectrum. The unique feature of MFCC lies in its uniform distribution of frequency bands on the net scale. This characteristic aligns these bands more closely with the nonlinear auditory system of humans, making MFCC a representation method that better approximates human auditory perception compared to conventional linear gestural methods. And this is the flowchart of emotion recognition system. The emotion recognition system is divided into two parts: speech emotion recognition and facial emotion recognition. In speech emotion recognition, audio files from the dataset are first processed to extract features that match human auditory characteristics using MFCC. Then we feed these features into a 1D CNN to extract more advanced features and identify emotions. For facial emotion recognition, video files from the dataset are first processed using MTCNN to extract face from the video. Then these extracted face videos are processed into frame-based image after frame blocking. Then these frame-based images are fed into the Gauss model to identify emotions. Finally, the results of the two emotion recognition systems are combined to achieve better efficiency. And we use two different datasets to train the model for the two emotion recognition systems. First is the reference dataset. It is a comprehensive collection designed for the study of emotional speech and thought. This dataset provides a rich variety of audio-visual data to facilitate research in emotion recognition and related fields. Reference datasets cover 8 different emotions, including neutral, happy, sad, angry, fearful, disgusted, and trust. The other one is Trinity dataset. It includes performance from 91 diverse actors, demonstrating a variety of emotions such as anger, disgust, fear, happiness, neutral, and sadness. And Trinity dataset comprises 7,442 audio and video files, each file representing a performance of a specific emotion. All video and audio samples are annotated with emotional labels and intensity labels. And next, I will introduce 1D CNN. This 1D CNN architecture consists of 8 CNN blocks, a fully connected layer, and a softmask layer. Each CNN block sequentially stacks and one-dimensional convolutional layer, a batch normalization layer, a pure loop acceleration function, and a dropout layer. The kernel size of the 1D convolutional layers in the first, third, fifth, and seventh CNN blocks is 5. And kernel size is 5 with a stride of 1. The second, fourth, fifth, and eighth modules and blocks have a original size of 7 with a stripe of 2. The first 6 layers have 128 filters each, while the last 2 layers have 64 filters each. A double layer parameter of 0.4 is included in the ceiling blocks to prevent overheating. Then we have 2 fully connected layers, one with 122 millivolts and another one with 8 millivolts. And using the softmax layer that converts features into a probability distribution to obtain the final switch motion accuracy. And next, in the facial emotion recognition part, the ghost module is the primary structure in the model. It is a model used to build efficient neural networks that can generate more feature maps from chip operations, thereby reducing the computational cost of convolutional neural networks. The ghost module splits the original convolutional layer into 2 parts, uses fewer filters to generate several intrinsic feature maps, and then applies a certain number of chip transformation operations to efficiently generate those feature maps. The ghost module can be used as a plug-and-play component to scrape existing convolutional neural networks. And instead of the ghost module, we also use tribulate attention module in the model. It is a lightweight attention mechanism used to compute attention weight by capturing cross-dimensional interaction between grid arrow branches to build interdimensional dependencies. Triggered attention has 3 branches. The top branch is responsible for computing attention weights across the channel dimension C and the threshold dimension W. Similarly, the middle branch is responsible for channel dimension C and threshold dimension H. The final branch at the bottom is used to capture special dependencies for threshold dimension W and H and W. In the first 2 branches, we adopt rotation operation to build connections between the channel dimension and either one of the special dimensions. Finally, the weights are aggregated by simple rules. Then we combine 2 stacked ghost modules with a triplet attention module to create the ghost bottleneck. The first ghost module serves as an expansion layer, increasing the number of channels. The second ghost module reduces the number of channels. And a triplet attention module is inserted between the 2 ghost modules. Then the input and output of these 2 ghost modules are connected using a shortcut connection. In the ghost bottleneck with a stripe of 2, a deadweight convolution with a stripe of 2 is added between the first ghost module and the triplet attention module. It reduces the size of the feature map by half compared to the input. Similarly, the shortcut path also undergoes the same dynamic. And based on the ghost bottleneck architecture and following the structure of neural B3 flow, we replace the bottleneck with a ghost bottleneck, incorporating the triplet attention module. The first layer consists of a standard convolutional layer with 16 filters. Then the subsequent layers consist of a series of ghost bottlenecks. Finally, we utilize global average Boolean to obtain the features from 15 frames image. After extracting emotional features from 15 frames image using GhostNet, these features are fed into the frame attention network. It can emphasize which frame features are the most informative for emotion recognition among the 15 frames. Frame attention network consists of 2 parts. The first part is self-attention weights, which are assigned to each frame through a fully connected layer and a symbolic activation function. These weights indicate the importance of each frame for the final emotion recognition. second part is the relational attention weight, which considers the relationship between individual frame features and global features. This is achieved by concatenating individual frame features with global features and then feeding them into another fully connected layer. After the input features are produced by frame attention network to obtain the final emotional features. We use the fully connected layer and softmax layer to convert the features into a completed fusion, thereby obtaining the final facial emotion output. And after obtaining the outputs from both facial and speech emotion recognition systems, the outputs are fused using geometric mean method to achieve better results. Facial and speech recognition system models may each exhibit bias in specific emotion computation. The geometric mean can smooth out these anomalies, reducing the impact of extreme predictions from one model on final result, leading to more stable predictions. When models from two different sources agree on the same emotion label, the geometric mean implies this increasing confidence in that label. This boosts confidence in the predictions for that label and reduces the major misjudgment associated with single mode recognition. And this is my result. And these are the results of the proposed method with the rendered dataset. The F1 score for the facial emotion recognition system achieves 90.79%. The F1 score for the speech emotion recognition system achieves 82.12%. After using geometric mean method to combine the results, the F1 score achieves 97.55%. And these are the results of the proposed method with the Primavera dataset. The F1 score for the facial emotion recognition system achieves 77.29%. And the F1 score for the speech emotion recognition system achieves 48.06%. And after using the geometric mean method to combine the results, the F1 score achieves 82.31%. And this table compares the accuracy parameters and graphs of the proposed method with the state-of-the-art method. Our proposed method requires only 0.92 n parameters and 0.77 g graphs. It significantly reduces the parameters and graphs while ensuring the accuracy is only 1 to 2% lower than the best method. And finally, the multimodal emotion recognition system was deployed on the companion robot Stable Geometry. The figure shows the CPU utilization when the emotion recognition system is running on Stable Geometry. During the operation of the proposed emotion recognition system, it occupied 50% of the CPU resource, bringing the overall CPU utilization to approximately 78%. This indicates that other advanced technologies, which have parameters and graphs tens of times larger than our method, are not feasible to run on Stable Geometry. And in this study, is my conclusion. In this study, and 1D CNN was used to construct a neural network for speech emotion recognition. The ghost model and triplet attention module were integrated into a new ghost AI vector, which was combined with the frame attention network to form a neural network for facial emotion recognition. The final combined result of the two emotion recognition models achieved accuracy of 97.55% and 82.33% on the versus data set and cumulative data set respectively. This study proposed a multimodal emotion recognition system using facial and speech features. It significantly reduced parameters and loss while maintaining a certain level of accuracy, enabling the emotion recognition model to run in companion level. And this is my reference. Thank you for listening.
Okay, thank you for your presentation.
Why do you demonstrate need to use the output of true emotion instead of other average methods?
Geometric mean will multiply the output first and take the square root. So using this method can reduce the impact of the string result and enhance the confidence in the label prediction from different sources are identical.
Thank you.
Thank you for sharing your research. And I have a question. You mentioned that at the end of the research, the emotional recognition system was deployed on a robot. Could you explain how you deployed it?
Simple Junior 2 is an Android-based robot. So I developed an Android application and I set the training model parameters. Then these parameters were used in the application.
Any questions? No? Yeah, one question from the floor. Okay, so in conclusion, thank you for your attention. Going to end today's lecture and then see you a week after next week.